We'll look at the specifics of the double replacement reaction. So in a double replacement reaction, we're looking at two ionic compounds in aqueous solutions that then switch with each other to produce some kind of new substance. The substance does not have to be insoluble, but the classic example is that it is insoluble. In the reaction video that you watched in PlayPosit, you saw the barium chloride reacts with potassium chromate. So let's go through and actually walk through the other one. And I think I actually talked through that one in a previous video too. So we'll go through it anyway. Sodium chloride. So sodium with chlorine, this is going to be aqueous, reacts with lithium nitrate, also aqueous. For those people that are still wondering, do I really have to know how to do that? Yes, you do. Okay, you have to be able to go from the names to those formulas. And this is going to somehow undergo a chemical reaction. In doing that chemical reaction, what we want to do is find patterns. So the patterns that I'm trying to show up above is that we're looking at our metals being listed first, followed by some kind of non-metal. In this particular case, we switched it up and made it kind of challenging because we've got our non-metal showing up as a single species in the case of sodium chloride and as a complex ion in the case of lithium nitrate. So if we're going to go through and swap those around, we're going to be slightly obnoxious on this, and we'll say lithium goes with the chloride, and we need to do a little bit more than a little more space, and then our sodium goes with the nitrate. Okay. For those of you really paying attention here, we said lithium was C, and you'll notice that the C one that I did, I put first. So again, the order that we do our addition doesn't matter. For an individual formula, though, we do need to ensure that our metal shows up first. Okay? So what we've now gone through is predicted what our products would be. According to our balancing rules, once we've predicted our products, we should ensure that the formulas we've used are correct. That means going through and checking each individual formula. Sodium is a +1, chloride is a -1. That formula would be proper and balanced. Lithium is a +1. Nitrate is a -1, and that's something that I would have to memorize, and I would highly encourage you to memorize it because you'll see it a lot, so it makes sense to have it memorized. Those charges balance out, so again, that one's okay. We move to the products. Lithium +1, chloride -1, balanced. Sodium +1, nitrate -1, balanced. Now that our formulas are correct, we could go through and try and balance out the entire equation. To balance the equation, just for the sake of practice, we would start with sodium. I prefer to go kind of underneath the reaction arrow. On the left-hand side, I have 1. On the right, I have 1. Chloride on the left, I have 1. On the right, I have 1. Nitrate, I prefer to balance as a complex ion because it didn't change, 1 and 1. For those of you asking why I skipped lithium, let's just say I did that intentionally just to mess with your heads. I just didn't see it. Okay, so there we go. And that would suggest that everything is balanced, so we now have our proper balanced equation. With a double replacement reaction, one of the last things that we are also expected to be able to do is to predict the phase of the products. Okay? That phase for both of these substances ends up being aqueous. The only reason I'm able to identify that that phase is aqueous is because I've memorized some solubility rules, which is what we're about to look at. You're responsible for knowing those, so you do have to be able to manipulate them. If it's something that you're really not going to commit to memory, that's okay, but make sure that you've got the solubility rules next to you when you go through and start exam 2, so that when you encounter a question where you have to predict those phases, you can very quickly reference the solubility tables to be able to get your answer. Again, practice that. You don't want to be experiencing on the exam for the first time, oh, I don't know how to read these, because you're going to waste time on completing the exam. Okay? So we've got the two equations. How would we know if a reaction occurred? Well, this goes all the way back to our predicting or looking at chemical changes and identifying the key characteristics: change in phase, change in color, and change in energy. The change in energy and the change in color, we aren't going to be able to see in a chemical reaction where we've written out the equation. Okay? So what we're looking for is the change in phase, because the change in phase is something that we're expected to include in our equation. And that change in phase is conveniently located in the parentheses after each one. So if we take a look at that first reaction, aqueous all the way through, there is no change in phase. If there is no change in phase, there is no reaction. No chemical reaction has occurred. For those people saying, but it looks like sodium is paired up with something else, again, because it is aqueous, it's not, technically not paired up at all. And it's free floating as an ion, which is what we talked about back with chemical changes with sodium chloride. It goes in as the ions when we hit that aqueous environment. Okay? So the top one would technically be a no change. In the case of the bottom one, aqueous goes to aqueous and solid. There's now a clear change in phase. That means a chemical reaction did occur. If we were asked to just balance equations where a chemical reaction occurred, the first one we didn't technically have to do. The second one we would have to, because we do have a change in phase. Okay? I do want to draw your attention to the kind of point here. That S, change in phase, is for solid. It has nothing to do with this word up here, and in particular, that S, soluble. Okay? That is a different observation. There is no acronym or symbol for that. Don't worry about it. What you're looking for is, did a phase change occur? Okay? So that's roughly the examples there. The next layer that comes to this is, how do you know what the phases are? That comes from looking at a solubility rule sheet. So this is what we've got here, our solubility rules. We walked through it in the past. I made a couple additions here. Soluble means aqueous, so the phase would be AQ. Insoluble means solid, which then means S, of course, for solid. Okay? How do we go through and use the table? So let's start with barium chloride. What I need to do is look for barium plus 2 and chloride minus 1. So I go up to my chart and start searching through that chart for either of those ions. There's chloride, barium. It's usually helpful to have people shouting in class where all the rules are. There's barium again. I think we've got them all. So if we go through and look at it, let's look at the barium first. Partnered with hydroxide, not the case, irrelevant. Partnered with sulfate, not the case, irrelevant. So now I'm going to look at the chloride. Halide ions and 4 follow under that rule. That rule said aqueous, so the phase should be aqueous. Before I get too excited, I do have to remember that there are sometimes exceptions. The exceptions to solubility would be insoluble, so a solid. So we would look at the exceptions: silver, mercury, and lead. We're looking at paired with barium. It's not an exception. It's going to be aqueous. Whoever wrote this out did a good job specifying that phase. Okay? That's the process that you should move through for being able to determine your solubilities. Again, when it comes to the exam, I don't expect you to have these all memorized, because I think that's kind of a waste of your effort. I do expect you to be able to interpret them. Okay? And there's 2 ways that you can potentially deal with that interpretation. One, you have your own sheet of solubility rules. By all means, go ahead and do so. Like I said, open note exams, there isn't a whole lot I can do. Okay, so you can have some solubility rules available to you. You can use these or find other ones that you like better. Okay, I personally don't like these. The other thing that I would highly encourage and recommend is that you actually memorize a few of these, okay? Because a few of them with a little bit of memory will now be able to get you through quicker than having to reference a sheet, probably 50% of the questions that you would analyze. So what do I mean? We have to look and very carefully memorize proper ones to deal with. So which of these 10 rules, and they're more like guidelines, do you think you should commit to memory? I'll give you a hint. There's only 3 that you should commit to memory. And conveniently, it's the first 3. Those first 3 are the only ones that I have ever bothered to commit to memory, and are the only ones that I would ever recommend someone commit to memory. Okay? And there's one very huge reason for why you should commit those and none of the others. What is different about the first 3 in comparison to the last 6? You can think back to your Sesame Street. Which one of these things is not like the other? I think I even did that somewhat in tune. Exception, 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 exception. The other 6 all have exceptions. Why do I want to commit to memory something that isn't always true? Because if it wasn't always true, I'm going to have to look it up anyway. Right? Okay. So you should commit to memory those first 3. I think that's easy. That's not that much effort. The rest, you just kind of have to accept that you'll look up. Okay? And so that's, my 2 cents as far as double replacement goes. It's really now just about practice on your end with going through those equations. I forgot. We do have a little bit more there. Neutralization reactions are tagged into this because if we look at our neutralization reaction in comparison to, say, how we set up the double replacement, our double replacement was what? AB plus CD. If we align this, there's the A with the D, and then we have the C part with the B. I know the other A's and B's get in there and kind of get in the way, but what you should be seeing here is that these 2 equations fit the format for double replacement. Okay? And a neutralization is actually a double replacement reaction. They're one and the same. The thing that makes the neutralization a little bit different on why we would call attention to it, there's really 2 things. Number 1, we're not really looking at solids. Typically, when we're looking at the neutralization, it's not a phase change to a solid, it's a phase change to a liquid. That liquid being right here at the end, which is written kind of weird, but that's to help see that placement, H2O. It's the formation of liquid water. That formation is what makes it roughly the equivalent of a solid. It's a new phase. Okay? So why would we talk about it? Well, water is incredibly common, so that's a good reason. We're producing more water, and we see that everywhere. The other big reason is the class of species that you're reacting. You're reacting acids with bases. Acids and bases as a class of chemicals are so well studied that any of the reactions that involve them tend to have some kind of special naming with them because we were looking at those classes and defining them for historically a long amount of time. And we will look more closely at these at the end of the semester. But really what we're looking at is the combination of 2 things. An acid, which you should be able to recognize as an acid because you'll see the AQ at the end and the H in front. And then bases, you'll be tipped off because you have the OH. Okay? And why would that be helpful? Well, if we look at the end product, it's H with OH, which is really just another way of writing H2O. So acids and bases are fancy because it's what happens when we split water. Okay? So acids and bases are really just the pieces that make up water. And that's why they get their own special reaction. Name is neutralizations. The equation set up here, sum of the coefficients for the reaction of barium hydroxide with phosphorus acid, is intentionally a new equation. So you should be able to go through and write it out, predict the products, and words balance the equation. Right, so I'm going to recommend that you hit that pause button for me. You have now come back because you totally understand what's going on with this, and you just want confirmation of your fantastic awesomeness. Barium, Ba hydroxide, OH. And actually, I'm going to change that up a little bit. I'm just going to do barium hydroxide plus our phosphorus acid. We know it's an acid, so we have the H in front. Phosphorus gets a bit tricky. It's going to be PO3. And then this is going to go through to make our products where we combine the barium with our phosphorus. Yeah, PO3. And then we would also produce our H2O. So if you got that, fantastic. Good first step, but you're not done. Okay? Remember our rules. We need to make sure that we balanced each of our formulas correctly. Barium is a +2, hydroxide's a -1. BaOH is not a proper formula. To make it a proper formula, I need 2 hydroxides. I have to include the parentheses so that that is very clearly 2 hydroxides to 1 barium and not barium water, okay, or OH2. We move to the phosphorus acid. The phosphite ion is a -3, hydrogen's a +1. Those charges don't balance. I need 3 hydrogens to balance the phosphite. We move to our product. Barium's a +2, phosphite is a -3. This is where things are going to get a bit kind of hinky. You just predicted that swap. And what I'm going to tell you to do is that you need to balance out those charges by changing the subscripts. Right? And what we've seen in the past is you shouldn't be touching those when you go to balance the equation. We haven't actually started balancing the equation. So we are okay to change those coefficients or those values, those subscripts. Once we start balancing the equation, then yes, do not touch them. You have to leave those numbers that are subscripts alone, because those are what identify the compound. H2O at the end could be a little bit tricky. Hydrogen's a +1, oxygen's a -2. There's 2 hydrogens though, so that does balance out the charge. Now that our formulas are correct, now we could try and go through and balance the equation. Barium 1 and 3, so I need a 3 over here. That's a 3. I'm going to balance this as hydroxide, which means I also need to write this out as HOH. And to help me out even further, I'm actually going to write it as HOH so I can differentiate those hydrogens. I have 6 OHs on the left, and I only have 1 OH on the right. To make that 6, I need a 6 in front. To balance out the hydrogen now, on the left, I only have 3. These hydrogens have already been accounted for in the hydroxide, so I don't count those in my total. On the right, I have 6, because of the coefficient 6 in front. To get that balanced, I would need to put a 2 in front there. This now becomes 6. I could now look at my phosphite running out of space. There's 2 on the left, and there's 2 on the right. I now have a balanced equation, and I've done everything that was asked of me by that silly, stupid instructor staring at me. And with that, we're actually done. Let's actually make sure. Yeah, cool. There we are. Thank you for working through that one.